Welcome to my YouTube channel. So today I will discuss subspace of a vector space. So for that, let's consider V be a vector space over the field K, and let W be a subset of V. Then W is called subspace of vector space V over the same field K if W is itself a vector space. Okay? So W is a subset of V and V is given already a vector space over the field K. Then we call W is a subspace of the vector space V if W is a vector space. Okay? So this is the definition of vector space. So there is a theorem to prove a given subset of a vector space to be subspace of V. Let V be a vector space over the field K, then any subset W of V is subspace of V over the field K if the following two condition holds. One is the zero element will be in W, or second one, for any two U and V belongs to W and a scalar from this K, the sum U plus V will be in W and the scalar multiplication, that is K into U, will be W. So if we take any two element from W and a scalar from K, so if you can show this sum contained in W and the scalar multiplication will contain in W and the zero element contained in this W, then we say this W is a subspace of the vector space V. So here these two, here this condition can be written as for any two UV from W and AB from K, if we show that AU plus BV belongs to W, if we can show this for given UV belongs to W and AB belongs to K, we can say W is subspace, and this is also have to be satisfied that zero element always will be the subset W to be vector space. So now you prove two theorems which are very important for your exam. So the first theorem is the intersection of two subspaces of a vector space V is a subspace. So first let us consider U and W be two subspaces of vector space V. So the theorem says that U intersection W is a subspace of V. So we have to prove this. So now this is just a subset of V. V is a vector space and these are two subspaces. So this now U intersection W is just a subset of V. So we have to prove that U intersection W will be subspace. So first property is the zero element. So as U is a subspace of V, so 0 belongs to U, and W is a subspace of V, so 0 belongs to W also. So from this 0 belongs to U intersection W. So the first condition is hold. So for second one, let us consider, so we have to take two elements from this intersection. First we take U belongs to U intersection W and V belongs to U intersection W and A comma B belongs to K. So we have to prove that AU plus BV belongs to U intersection W. So we will prove this. So whenever we take this, so from this we get U belongs to U, also U belongs to W, and from this implies that V belongs to U also V belongs to W. Okay? So as U belongs to intersection, so it will contain in U as well as W. Similar case will happen for this. So U belongs to capital U belongs to W, and this. So from this, and this is scalar in K. So we get this, okay, 1. U belongs to U intersection W. So this gives U belongs to U and U belongs to W. Similarly, V belongs to U intersection W implies V belongs to U and V belongs to W. So this is 1. So we have to prove this. And AB also belongs to K. So as U is a subspace of V, so U belongs to U, V belongs to U, and A comma B belongs to K implies that AU plus BV belongs to U. Okay? So this is 2. Similarly, we get U belongs to W, V belongs to W. So as W is a subspace of V, U belongs to W, V belongs to W. So this is W. U belongs to W and V belongs to W. So as W is a subspace of V and we get U belongs to W and V belongs to W and AB belongs to K. So from this we get AU plus BV belongs to W. So this is 3. So from 1 we get AU belongs to U, from 2, and from 3 we get AU plus BV belongs to W. So this same element belongs to U and W. So therefore AU plus BV belongs to intersection of them. So what we assume at first? So we assume that U belongs to intersection, V belongs to intersection, and AB belongs to K, and ultimately we get AU plus BB belongs to intersection. So we can conclude that this U intersection W is subspace of vector space V. Okay? So this is the proof. So I will take one more theorem. From this theory, you can conclude that, sir, as corollary, intersection of any number of subspaces of a vector space V is a subspace. So if you take any I equal to 1 to n, so if you take this is Wi, so this will be subspace whenever each Wi is subspace of a vector space. Therefore, the intersection of n W, that is W1, W2, Wn, will be subspace of V. So let us take second theorem. The solution set W of a homogeneous system X equal to 0 in n unknowns is a subspace. So if we find a set W which contains xi for which axi equal to 0. So this is solution space of this homogeneous system X equal to 0. So this will be each xi is written as k1, k2 dot dot n to k. So this is a subset of Kn. As Kn is a vector space, so if we prove that this is a subset, so then it will become subset of Kn. So for that, as this A comma 0 0 0 n n n 0 is equal to 0, that is 0 0. So 0 element belong to W. Okay. So first is hold, and the second one, let us take U and V belongs to W and AB belongs to K. So as UV belongs to W, so AU equal to 0 we get and AV equal to 0 we get. So now we find that AU plus BV will belong to W or not. So to show that, we have to show this A into this equal to 0. So now we find this value. So this will give you A, AU, A, BV, that is A, AU, B, AV. So this is 0 as UV are element from this solution space. So this will satisfy this. Therefore we get this 2. So this will 0. So A0 B0. So this will 0. So we get AU plus BV equal to 0. So this implies that AU plus BV is a solution of the homogeneous system this. So therefore this will belong to W. So W is a solution set of homogeneous system x equal to 0. So therefore we can conclude that W is a subspace of Kn, where W is the solution set of homogeneous system x equal to 0. So for today that's it. I will discuss more about vector space. I will cover the chapter vector space and we'll cover some previous year question. So if you like it, please share with your friends. It will be very beneficial for the students of Triple IT Bhagalpur first year. So keep watching, keep learning. Thank you very much.